Let's put our new definition of definite integral to work. We'll work on the same velocity driving problem we've had before. What's the integral from 0 to 2 of v of t dt? Here's a copy of our graph. We can highlight a region. So what region are we talking about the area under the curve for? It's from 0 to a half, and we'll cross-hatch it like that. And what is that area? Well, it's a height, v of t in that region is 50, and the width is 1/2 minus 0, and that's height times width. Of course, it's not really a height, it's 15 miles per hour, but in our area kind of model of what's going on, it's like the height. What's the integral from 1/2 to 1 v of t dt? It is from here to there. So let's crosshatch that the other way. And that is a height of 40 times a width of 1 minus 1/2. The exact arithmetic isn't all that important here. How about the integral from 1 to 2.5? Well, here's 1, and 2.5 was somewhere in the middle here. And I'm going to crosshatch that maybe just horizontally. So that's a height of 60 and a width of what? 2.5 minus 1. Isn't this almost feeling like tangent line formula stuff? Something times x value minus other x value? That's kind of interesting. Then let's try it here. What's the integral from 0.5 to 2.5? Well, here's 0.5. Here's 2.5. Can I just say, well, that's a box height times a box width, but it's not all one box, right? I could kind of guess or eyeball an average height, which would give me a pretty good answer, but it turns out I don't actually have to do any new work. What I can say is this total area is the sum of that area and that area. So we can do the cross-hatching like we did there, and the cross-hatching like we did there. So that's the sum of these two. So that one and that one. So we actually don't have to do any new work other than adding two things. So that's an example of taking a complicated problem where we don't have a constant height and turning it into two smaller, simpler problems and then putting it back together. Another way to say what we just did is that this integral, we did part of it, stopped, and then went and did the rest of it. So we could say the integral from a to b v of t dt is the integral from a to some other number, we'll call c, v of t dt, plus picking up right where we left off at c and going to b, v of t dt. Here I'm writing it for velocity, but it's true for any function. And to diagram what we were doing, we had 0.5 was here, that was A, 1 was here, that was C, and 2.5 was here, that was B. It's kind of frustrating that they aren't in alphabetical order. But we're saying this should be true no matter where you stop the integration and then start it again. And it turns out to even be true if C is not between A and B, which is another interesting story we'll have to get to later. Next, we'll try a shape that's more interesting than that and also more familiar.